Okay, any other questions on the material? So last time I was giving kind of a big picture on what happens when we start looking at the molecules. I gave the molecular Hamiltonian, right? So it's a relatively lengthy but relatively straightforward object. It's one of the simplest things in molecular quantum mechanics, how to write Hamiltonian. And so the point of writing it so that we can at least formulate what the time-independent Schrödinger equation for a molecule will be. So now we stated that molecular Hamiltonian consists of kinetic energies of all particles, electrons and nuclei, plus potential terms, right, which is Coulomb interaction, and this is kinetic energy, right? Okay, and we also at the end stated that well, the problem is not exactly solvable. It's like the analogy with algebraic problems would be if you go beyond the 5th degree polynomial, you don't have always ways to solve algebraic like equations like quadratic, but of the 5th or 6th power. They cannot be solved exactly analytically. So similar situation with the time-independent Schrödinger equation. For molecules, the only molecule which allows the analytic solution is H2+, which is hardly a molecule, but yet whenever you have more than one electron, then the problem is not solvable anymore. Actually, even H2+ is solvable only for the electronic subsystem. For the whole molecular Hamiltonian, it's not solvable because it contains 3 particles. But we'll get to that in a moment. So the main idea is that this is not exactly solvable for general molecule, and more than that, even numerical solution is hard because we have the wave function, which is a function of 3n e variables from electrons, and also there are also nuclear variables, right? 3n nuclear variables, and so together this is a 3n number of electrons plus number of nuclei. So that's the number of dimensions that we need to consider, even if we just like to write down what this function is. And a simple estimate, if you have 10 points per dimension for a molecule like CH4, you would have 10 to the 45 points to keep. And so if you build the, say, the storage, these DVDs, and standard DVDs like 1 gigabyte of roughly about 1 to 4 gigabytes of information, and so 1 gigabyte is roughly 10 to 9, right? 1 billion bytes, so 10 to the 9th. Then you can calculate how many DVDs roughly you would need to store this amount of information. 45 minus 9 is 36. 10 to the 36 DVDs that you would need to use, and if the one DVD weighs even a couple of grams, right, or let's say 10 grams, then it's 10 to the 37 grams you need to of matter you need actually to store this information, and probably the weight of the whole Earth is less. I don't know exactly, but probably it's less. So you won't even have, if you use all the atoms from the Earth, you won't be able to build a number of DVDs that could store this information just for the methane molecule, right? So that's not the largest molecule out there. Now, this is a problem. No one actually solves and stores this information for even simple molecules. So what people usually do, they use some approximations so that storing and solving the equation is more manageable, right? So today we'll talk about one of such approximations, which is called Born-Oppenheimer approximation. So Born-Oppenheimer approximation. Okay, so Born and Oppenheimer came up with this idea to separate electrons and nuclei, and to solve the problem, namely this problem, time-independent Schrödinger equation. Right? Although this approach can be used for time-dependent as well, but let's focus on time-independent. So the idea is we have too many variables to consider, right? That's the root of all evils, that we need to solve differential equation for that many variables. And more variables you usually have, more things to store, and harder to calculate the solution. Okay? So what Born and Oppenheimer did, this very kind of intuitively simple idea that follows from the just classical intuitions. Electrons are light, nuclei are much heavier, right? So mass of electron in the atomic units is 1. Mass of nuclei, like the lightest nuclear proton, say, essentially that's the nucleus of hydrogen, that is roughly 2000, right? Okay, atomic units. So there is a 10 to the 3 power difference, or 3 order of magnitude difference between the mass of the lightest nucleus and the electron. So therefore you can classically think, okay, lighter objects, if they are provided enough energy, then they move much faster, right? And the kind of heavier objects, they will be much slower. So kind of reasonable approximation would be then we consider what electrons do when the nuclei are static. Okay, so if they move much slower, then we can consider them static. And then when they move, then we'll reconsider what electrons do, and so on and so forth. So the situation is like, if you can imagine a cow on the summer lawn, and lots of flies around the cow, right? And the cow is kind of a slow subsystem that corresponds to nuclei, and the flies are fast subsystems correspond to electrons. So the electrons are adjusting, or in this case flies are adjusting while the cow is moving along the lawn, and it's grass, and well, two systems kind of they are attracted to each other. That kind of attraction that comes from the electron-nuclear Coulomb attraction, right? In the case of molecules. Also, in general, we talked about the separable operators, which are like these nice operators. If you consider problem where Hamiltonian is operator for one particle plus operator for another particle, and there is no operator that mixes them, right? So there is no such term. Then you can solve problem for this, you can solve problem for that. Essentially one particle, and then you can combine the solutions of those two to make the solution of H. That was the case for the, say, particle in a two-dimensional or three-dimensional box, or you can also think of it as two particles which are not interacting in one-dimensional box. Right, so that was easy. Now for molecules it doesn't work because there is the coupling, electron-nuclear coupling, so you cannot really solve the problem for electrons and then solve the problem for nuclei and combine them together, get the solution for molecules. That won't work. on a physical level, that is very clear. If you try to bind electrons together, they are all negative, so they will fly away from each other. If you try to combine the nuclei, they will also be all positive and will fly away from each other. So they really need each other to form molecules. Okay, so therefore, even like if you start thinking in terms of variational approach, and you may try to, for the situation where there is a coupling like this, you may try to solve the problem for this operator, solve the problem for that operator, and then since they can kind of create, the solutions are creating some kind of a complete set, then you can try to solve the total problem with the coupling by optimizing the coefficients, right, in this problem, so that they minimize energy, and finding these coefficients will allow you to kind of construct a wave function for the operator which contains coupling, right? So that is also a feasible approach, even if you have coupling. That's why variational approach is so powerful. It can address problems not only with separable operators, but non-separable. The problem with this, just trying to apply this to molecules, is that what I just already said. If you try to build the solution for electrons without nuclei, and if you try to, this would be these guys, and if you try to build the solution for nuclei without electrons, this will be, well, I can tell you what this will be. This will be plane waves. So this will be very delocalized wave functions. Now, how do you build molecules which are localized objects out of the waves which are very delocalized, essentially, that are spanning the space from -infinity to +infinity? How do you do that? You need a lot of these functions so that they cancel each other at infinities, and they kind of interfere destructively there and constructively at the molecule. So you will need a kind of infinite number of them in order to do this kind of tricks. So it's not going to be very practical, because the complexity of problem to find this coefficient, it grows very quickly with the number of indices that you need to account for accurate solution. And the point is that if you want to draw a cow using only squares, then it will take a lot of squares to draw a cow, right? So you need some curves, you need something that is close already by its image to a cow, so that you can combine in those things, create a cow image, right? So here we have a kind of image of the molecule which is localized. We're trying to build it out of the waves which are delocalized. So just it will take a lot of them to build the localized molecule. All that is kind of telling us that we should not separate electrons and nuclei just blindly taking electrons out of nuclei, out of molecules, or taking nuclei out of molecules, right? So what Born and Oppenheimer did, they came up with a smarter scheme. They defined what electron Hamiltonian is first. And electron Hamiltonian is essentially molecular Hamiltonian minus kinetic energy of the nuclei. I use small n. Okay, so that would be electron kinetic energy plus electron nuclear attraction plus electron repulsion plus V and N, which is kind of counterintuitive. Why do we leave the nuclear repulsion in the electronic Hamiltonian? But you will understand why in a moment. So what this electron Hamiltonian does, it depends on the electronic coordinates, which I will denote as small r. So small r is essentially combining all r1, r2, r up to r and e. So in order to skip writing all that, I'll just write small r vector. All right, so this vector contains other vectors in itself. And also because, well, this term and these terms, they will contain big R, the nuclear coordinates, right? So this electronic Hamiltonian will depend on the nuclear coordinates as well. Now, the advantage of removing the kinetic energy of nuclei from the consideration is that now we can freeze the nuclear coordinates. Before, in the full molecular Hamiltonian, we had terms like essentially derivative second derivative with respect to nuclear coordinates, right? That's what was constituting the kinetic energy of the nuclei, right? If you freeze nuclei, you cannot consider such terms because those are kind of derivatives, and you cannot make big R as parameters. So therefore, Born and Oppenheimer, what they did, they removed the kinetic energy of nuclei, and now we got the object that depends on the electron coordinates as coordinates, and the nuclear coordinates, which are frozen, now they are parameters. So what parametric problem do you know from the high school? Do you know any? Well, I'm writing the... Do you know what parameters are? Huh? Do you know the difference between coordinates and parameters in math? One says parameter, what kind of image do you have in your head? Or it's like blah, 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 blah. No, Born-Oppenheimer, blah, 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 blah.
Area, not a specific point? Or
what?
Like an area, coordinate is like a specific point, right? Like parameter is like an area? Or?
Oh, both are wrong, essentially. Okay. Yeah, forget about all this. Coordinate is not the point, coordinate is a coordinate, and point is just a value of the coordinate in a specific point, right? Coordinate, when I talk about electron coordinates, those are coordinates that are x and y directions, okay, right? So they are not points. Now, parameter is closer to point because they are fixed, right? You were saying something? Like an asymptote. Asymptote is kind of the also some value essentially, right, which goes parallel. But now the kind of the simple definition of what parameter is, it is a variable that is considered to be a constant in a certain scope. Just to give you an example from high school, my favorite. So everyone studied how to solve this, right? So here, x is a variable. And a, b, c, they actually can be also made variables. Like, who says that they should be something else? They also can be variables. But when we solve quadratic equations, a and b and c, they are fixed, right? Because it's only this solution that you learn, like what is the value of x that makes this true, right? So we know it's minus b plus minus square root of divided by b squared minus 4ac, right? Divided by 2a. So this is all correct only when a, b, and c are fixed, right? So when a, b, and c are fixed, this is x that makes this true. Now, if we change a, b, and c, then, well, the value of x will change, right? So this is a general expression. Now, when we go and solve the actual equations, whenever we solve them, we do not consider a, b, c as some variables. We consider them as constants. Like we can consider the equation like this, for example, right? And we can get the solution. So this is the scope while we're solving this equation. A, b, and c, they are fixed. They're 3, 5, and 7, or 3 minus 5 and 7, right? Once we solved it, we can consider, okay, well, what will be the solution if we change 5 to 5, from minus 5 to minus 6, okay? So what will be the solution then, right? So we went outside of the scope of the solving the equation, and then we can treat b now as a variable. But if we want to know value of x that makes this 0, we need to fix a, b, and c. Now they are parameters. We are solving for x, and this is the solution, okay? Now what Born and Oppenheimer did, they fixed the nuclear coordinates. Now nuclear coordinates is like a, b, and c, and what they're solving is differential analog of the algebraic equation that you solved in high school. Now this is our a, b, and c, the big r's, and we're solving differential equation with respect to small r, and the differential equation is pretty much the same than the kind of as we considered before. It has fewer terms. Before we had the kinetic energy to consider. Now we have only kinetic energy of electrons and all the potential terms. And in the potential terms, the nuclear coordinates, which were coordinates before, now they are fixed to some value of parameters. And in the lab, which will start next time, in the next Monday, what mainly you will be doing, you will be putting molecule in the program Gaussian, and you will be solving this essentially time-independent Schrödinger equation for electrons. That's right. So you fix the structure. Fixing the structure of the molecule means that you define the big R's as a parameter. So in case of methane, our old example, say if you put carbon at three-dimensional coordinates 0, 0, 0, then this hydrogen, say, will be 1, 0, 0, and this hydrogen will be some other coordinates, and this hydrogen will be another coordinates, and this hydrogen will be another coordinates. So all these coordinates, they are essentially big R's. Big R corresponding to the carbon, big R corresponding to first hydrogen, second hydrogen, third hydrogen, fourth hydrogen, and they're all fixed. Once they're fixed, we are considering this equation as like particle in the box problem, where R can be compared to the size of the box. When you solve particle in the box problem, the size of the box is fixed. That's parameter. That's a simple example of differential equation with a parameter, size of the box. Here, nuclei kind of form skeleton of the molecule, right? And they are fixed. They are parameters. All right, so this is what they suggested, to consider first what is the behavior of electrons when the nuclei are fixed. Okay? And then, once this problem is solved, and it's not exactly solvable problem as well for molecules, but with the computers you can solve it. It's just easier to solve this problem than the problem where all small r's and big r's are variables. Here, the simplicity of this problem stems from the fact that the big r's are fixed. We don't change them. It's like if someone asks you, solve me quadratic equation, but A, B, and C are not fixed. So what do you get? You actually, instead of having two solutions, one x and another x, right? That makes this 0. If A and B and C are not fixed, you have 4 variables, A, B, C, x, 4 variables, one equation. That means one equation removes one variable. So you get 3-dimensional manifold. It cannot be even imagined because we live in 3-dimensional space. Right? So we can imagine the 2-dimensional manifolds, but 3-dimensional manifolds, you need a 4-dimensional space to just draw it. Right? So this problem becomes very difficult if A and B and C are not fixed. This is like molecular Hamiltonian problem. But once we fix A and B and C, it's manageable. Even without going to university, you know the solution. Now, that's what kind of Born and Oppenheimer did for problem for the molecules. They suggested, oh, let's just consider electrons first. Now, if we do that, then the total wave function, which is a function of both electron and nuclei, it still needs to be expressed as some electronic function. We can use now electronic functions that obtained from the solution of electronic equation. And this electronic function has dependence on the nuclear coordinates, because when we change, say, position of this hydrogen, if we study some rearrangement in the methane molecule, if we change that, this equation, what will change? The Hamiltonian will change, the eigenfunctions will change and eigenvalues will change. It's the same as changing the box size in the particle in the box problem. Everything, energies and eigenvalues will be different. So there is a nuclear dependence here, but that nuclear dependence is fixed by this equation, so it's not enough to present the total nuclear dependence of total electron nuclear wave function. Therefore, we will put an extra function chi of r, which we are about to find. We don't know it yet, but we will find it. Okay? So this is just a construction. You can think of it as variational ansatz. Now we know this function from the first part of the problem, and we want to find this function. In order to define this function, we add extra function in this product, and we will find an equation for this guy. Once we find the equation for this guy and solve it, then we know the total solution, right? That's the plan here. Essentially, the structure is the following. We are interested in the total wave function that is a solution for the total problem. I use phi n for them, but let me just then define what I mean by psi. So what psi does, it's an approximation for the total problem, right, with molecular Hamiltonian. That's what we're looking for. Okay? And it will be approximated, so I have no right to write that it's exactly the product, because it's not. Okay, so we're looking for approximation for the total wave function. And the way we do it, we first define a small electronic problem, where we fix nuclei, right, and we solve for the electrons. Now the advantage of that is that we didn't remove the nuclei, right? They're still there. They're just fixed. They are not considered as variables. And that's a big advantage, because the molecule is still have a skeleton of nuclei on which there is a quantum flash of electrons are put. Right? So these are variables. Now, once we solve this problem, electronic problem, we have the electronic wave function. And it provides both electronic dependence and nuclear dependence. But nuclear dependence is not complete. And therefore, we add an extra function for which we will try to write equation first. And that will be A. And then B, after solving the equation, we will know chi, we know phi from electronic problem, so that we can approximate the total nuclear electron wave function. Yes.
But you don't know chi, right?
Yeah.
You're looking
First, I will derive the equation for chi, and then.
But you're not going to derive it using like the psi and the phi. You have to like.
You'll see in a moment. The next step is let's derive the equation. So how do we derive the equation for chi? And the approach is actually quite common in the quantum mechanics. I'll just show you, and this is probably the first time you see it, so I'll go slow. What we do, we start with the equation we know. This is a full-time independent Schrödinger equation. And molecular Hamiltonian is here, we can now write as electronic Hamiltonian plus kinetic energy of the nuclei, right? So it has two operators. Now phi is defined, we want it to be a product of phi, the one that we know, times chi, the one that we don't know. And we want this to be some constant, multiply again by phi and chi. All right? So technically, this is equation for chi, because phi is known, right? And chi is contained in the left-hand side and in the right-hand side, right? And it's not like something like chi equals to chi, right? So it has it is something meaningful, because there is a kinetic nuclear operator that will act on chi differentiated twice, right? So it will be some kind of differential equation, right? We already achieved something, but to make it even simpler, actually what helps is to multiply this equation from the left by phi star and integrate over all electronic variables. So that's kind of the treatment we do here. We multiply this left-hand side and, of course, right-hand side by phi star, and we integrate left-hand side and right-hand side with respect to all the electronic variables. So what do we get? So we got integral of phi star h electronic phi plus, and then there's a chi, of course, plus phi star Tn phi chi equals to integral dr phi star e phi chi. Okay? Now, there are lots of simplifications we can make because we know that electronic Hamiltonian, when it acts on phi, it gives us E phi back, because phi is an eigenfunction of the electronic Hamiltonian by construction. Okay? Now this E is a different E than this one. This one is just a constant. This E, the one that comes out of electronic Hamiltonian, let's put the subscript E. This is a different object, and it will have a big meaning later because it depends on the nuclear coordinates. So it's electronic energy which depends on what nuclear configuration do we consider. You, in general chemistry or in kinetics, you already been accustomed to that concept. When we study reactions from A to B, there's a transition state, right? So that those curves that people draw, this is electronic energy, essentially. This is energy of electrons for a specific nuclear configuration. So you change the nuclear configuration along the reaction, and you know from that quantity how unhappy electrons are, because you change the nuclear configuration. So they are happy in the minimum, right? And then you start changing the nuclear configuration. According to this equation, you will be getting different values of that energy. And you will see, okay, electrons are not happy here, not happy, even less happy here, even less happy here. But eventually you get to the, or maybe to make it more interesting, say, we can get to the more stable configuration when we go over the barrier, right? And the catalysts are compound that change that configuration because, well, when you add the catalyst, there are more atoms in the system, and the potential energy profile can be different. Of course, this is an all multidimensional plot. I really need to show here because it's all in the nuclear coordinate space, and that space is multidimensional. I'm really simplifying here by considering only one reaction coordinate, right? But that's what in chemistry we do. We were looking for one, maybe two reaction coordinates and try to describe difficult chemistry with just a one-dimensional plot. All right, so going back to this, you have electronic energy phi star. As we know, all the kind of Hermitian operators, and this one is not kind of exception, all of them have eigenfunctions which are orthogonal and normalizable. So what we can easily prove is that the integral over all the coordinates, right, of electronic function for a specific nuclear configuration with itself, that thing will be 1. And I guess I'm not writing the electronic subscript here, but potentially we can write everywhere electronic subscripts. All right, so what this allows us to do is, considering this term, it allows us to simplify the whole term to be just the electronic energy, which is a function of R, multiplied by chi with a function of R, and that's it, because the rest is just an integral over phi squared, which is 1 by that relation, right? So this term is simply this. Now, second term is here. And this is what the key approximation of Born and Oppenheimer actually is. The approximation here is that we have a kinetic energy and it's a differential operator, right? So it differentiates the nuclear coordinates. Now, we have two functions, electronic and nuclear. Nuclear is the function that is like a function, normal function of the nuclear coordinates. No question, this kinetic energy operator will differentiate that. But should this differential operator act on the electronic function? Why? Was that no or no? Huh? Why? Yeah. Yeah, but we have nuclear dependence in electronic coordinates. Sorry, not in electronic coordinates, in electronic wave function, right? So it depends on the nuclear coordinates. Technically, it should operate.
Doesn't the kinetic energy operator include, if you're saying it's static, right? So
But remember, I said, like in the case of quadratic equation, A, B, and C are static only when we solve it. But if we go outside of the scope of the solving, just we think, okay, what will be the changes in the, essentially technically the solution of quadratic equation is x, which is a function of A, B, and C, right? And now someone comes with a derivative operator with respect to A. Should we differentiate x? It is a function of A, B, and C. So technically we should differentiate x. If, say, you want to know how quickly the solution of your quadratic equation changes with A. So what do? You have A equals to 2. You solve it. You have a solution. Now the question is, okay, so if you step 2.1 and step like to the negative values, like take 1.9, right? So what's the difference in the solutions between 1.9 and 2.1, right? So is it a big difference or small difference? The derivative would be able to tell you without doing all these silly steps. So technically, if you want to know derivative, you can differentiate because x is a function of A, B, and C. A, B, and C are fixed when you solve for x, but after you solved it, you can analyze what x is a function of A, B, and C. Now here, Tn technically should affect both electronic function and nuclear function, but because it says Born-Oppenheimer approximation, right? Not Born-Oppenheimer theory. Approximation says that we ignore operation of the kinetic energy on the electronic function, and the reason for that ignorance is that the electronic functions behave very slowly. They change very slowly with the nuclear coordinates. Okay, so practically, if I would be able to draw the electronic function, which is a function of electronic variables, and also depends parametrically on nuclear, but imagine it would be just one value depending on the nuclear coordinate r, So that value would change slightly with big R. So then if it's a slight change, if you differentiate it twice, anything that is close to a line will give you 0, right, as a second derivative. So that's what is assumed here, and it works very well for molecules. You can ignore second derivatives of the, or first derivatives of electronic wave functions. Okay, so this term, technically you should get 3 other terms, because this is a kind of the second derivative of the product, and second derivative of the product will give you 3 terms. Two times differential of this function multiplied by this function. Once you differentiate this function, once you differentiate that function. And the third term would be no differentiation here, but all 2 are differentiated here. So that's the only third term we keep. The others are gone, right? And essentially what we have is the integral of the electronic variables Fe. So we kind of move the Tn through the electronic function. So this is 1 again, like here, and we have kinetic energy acting on the nuclear function. That's from that term. And this term is very simple. E is a constant here. It can be taken outside of the integral. Chi depends on the big R, so it also can be taken outside of the integral. And the integral is just a normalization integral, the same as here. And so the third term is simply constant multiplied by chi of R. Now we can write the equation for chi, which is going to be looking a little bit friendlier. So it's kinetic energy plus potential like term chi of R multiplied by constant E, right? So that's a nuclear counterpart, nuclear problem essentially, nuclear problem. So it's nuclear counterpart to electronic problem. So you see what Born-Oppenheimer did. They smartly split the total problem into 2, which both are meaningful. In one, they fixed nuclei like parameters. So for the electrons, obtain electronic energies, which form the potentials. And then the second one, after doing some approximations, they derive equation for the nuclear function that completes the construction for the total function. And that nuclear function is, again, kinetic energy plus potential term. And potential term comes from the electrons, right? So they are essentially driving the nuclear dynamics, or nuclear, they define the nuclear equation. Okay, so that's pretty much all. And what I would like to say about this problem is that this problem gives rise to all the vibrational spectroscopies, because vibrational spectroscopy pretty much is about finding the eigenstates of this problem, right? So this electronic energy, when you solve close to the minimum, say there is some equilibrium configuration of molecule, you have electronic energy. Since it's a minimum, the first derivative of this function, if you do the Taylor series expansion, right, so then you get at equilibrium plus the first derivative of the minimum in the minimum, what is it? 0. So you don't have first order term. The first term, which is non-trivial, is the second order term. So you have a second derivative, which is proportional to a frequency of vibrations. And because it's kind of it's with 1/2, is the coefficient of the parabola, because it's in the Taylor series expansion, this is the term. And then there are other terms which correspond to unharmonicity or deviation from this quadratic behavior. So we ignore them for simplicity for now. And this approximate view of the potential is just parabolic. And then the next topic actually after midterm will be harmonic oscillator, which is the kind of paradigmatic example for all the vibrational spectroscopy. So you will have some levels to consider that are formed by this equation with the quadratic function in the potential. And then when the, say, IR or Raman spectroscopy is done, system initially is some kind of ground state, and it's promoted to the excited state, right? And that energy difference corresponds to the simply h bar omega. So that's proportional to the frequency, and you can excite different bonds in the molecule and see the IR spectrum depending on your energy range. You have different intensities, and you get the essentially vibrational spectroscopy out of it. So that is coming from the nuclear part, but of course it's all impossible unless you solve the electronic equation first that you will be solving in the lab sessions, right? Any questions about this?
So you got the equation for chi, right? So
yeah.
Now you have to just insert the equation to get along with the electronic function to get the total.
Yeah, once you solve the electronic equation, then you can formulate the nuclear equation, because it requires this component, right, that comes out of electronic problem. And once you have this operator, then it's a just eigenvalue problem, only for the nuclear variables. So now electronic variables are not anymore present. They are, you can think of it as, physicists have this term integrated out. So we remove them by integrating over them, right? And the problem, this problem and that problem is simpler than the total problem. But of course we made some approximations, all right? We are not going to discuss much the nature of those approximations or how valid are they and where are they valid. We'll just well, for 99% of the chemistry they are good, especially for the chemistry that is done in the absence of light. Like in photochemistry, frequently these approximations are not working, and you need to consider more general theory. Also, one thing to remember is that this and that is an eigenvalue problem. What that means is that there are multiple solutions. So what I here didn't emphasize much is that there is also subscript n that enumerates electronic states, right, and electronic surfaces. So what I was discussing is mainly ground state, the lowest one, right? But for every nuclear configuration, you have infinite number of these states, right? But those are involved in the high energy processes. Like if you have light that excites molecule, then usually the light excites electrons mainly, and then different states are involved. Now for the vibrational spectroscopy also, you have here it becomes kind of a little bit tricky, because there is one subscript for the electronic state, and I call it n, and then of course the chi's, they are also enumerated. For every n there is an infinite number of chi's that are coming as a solution of this nuclear equation, right? That corresponds to the levels. So say in the simplest possible way, we can write this as different electronic states are just different parabolas, and every parabola has extra levels on top of them, which are going from the bottom of parabola to infinity. And so since you have multiple parabolas, or infinite number of parabolas, you have infinite time, infinite number of levels. Okay? So that's kind of a complexity, and it's after approximations actually. That's the complexity of the quantum world. All right? Okay then, that's it for today.